Good evening, everybody. Jonathan Gagne is a scientific advisor at the Rio Tinto Alcan Planetarium in Montreal and associate professor at the University of Montreal. He completed his PhD in astrophysics in 2015 and moved to the Carnegie Institution for Science in Washington, DC, for a 3-year postdoctorate as a Sagan Fellow. He came back to Montreal to start a second postdoctorate at the Institute for Research on Exoplanets before he was hired by the planetarium. His expertise is focused on brown dwarfs, young stars, exoplanets, and stellar associations. He uses various telescopes throughout the world, very lucky, and throughout the world to carry out his research, from the Observatoire du Monde Mégantic in Quebec, the infrared telescope facilities in Hawaii, and Gemini South in Chile. Since the launch of the Gaia Space Telescope by the European Space Agency, he uses these new data to discover the still missing smallest stars in young stellar associations. This allows the scientific community to better understand the fundamental properties of these small stars. It is a crucial step to then understand the properties of exoplanets we find in orbit around them. Jonathan is a member of a few international collaborations, such as Backyard Worlds, Planet 9, which concentrates on the discovery and study of brown dwarfs. His research projects led him to discover one of the first brown dwarfs, which masses are so low that they are similar to a gas giant exoplanets, except that they float freely in space, instead of being found in orbit around a star. These rare objects are sometimes called planemos. Is that the correct pronunciation? Thank you.
Yeah, planemos.
Thank you. In his free time, Jonathan is a total coffee freak and enjoys perfecting his barista skills while employing methods to draw the full potential from coffee beans from different origins around the world. So please put your hands together and give Jonathan a Mixed Swinton Astronomical Society welcome. Thank you very much.
Thank you. Should I go ahead?
Yes, please.
Awesome. Thank you so much for having me. I'm going to share my screen and see if that works. There we go. Let's start the presentation. Can everyone see correctly?
We can see that lovely, Jonathan.
Awesome. So I'm going to talk to you about stellar associations and planemos, and I'm going to explain what those are and why they are helpful to better understand exoplanets. So let's start with brown dwarfs. Those objects are sometimes called super Jupiters. You might have heard about them, but they're not that well known so far by the general community. They actually have similar atmospheres to gas giant exoplanets and also gas giants in our own solar system. One example is Jupiter. So they have similar cloud patterns, for example. However, they are more massive. So they have a lot more mass. They are approximately the same size as Jupiter. So that means they are actually more dense than Jupiter. And they are still less massive than stars. So they are kind of in between giant planets and stars. They are the objects that bridge the two different groups of objects. They can be found either in orbit around a star or just freely floating around, so a bit like stars. So we can find brown dwarfs that are just similar to stars. They're just floating around or around stars, just to recapitulate. When we say that something is freely floating around, what we actually mean is that it's on a very large orbit around the Milky Way. So the Milky Way is our galaxy. This is what happens when we find a star flying around. The star is actually on a very large orbit around the galaxy. So is the sun and all the stars in our neighborhood. So we can actually find brown dwarfs that are similarly just in orbit around the galaxy. So as I mentioned, brown dwarfs are kind of some kind of bridge objects between giant planets and stars. We can define that in terms of their masses. So the International Astronomical Union has adopted a range of masses that correspond to brown dwarfs. So typically the range that is adopted right now is 13 to 75 times the mass of Jupiter. So anything that is less than 13 times more massive than Jupiter would be called a giant planet. And anything that's more massive than 75 times the mass of Jupiter would be called a star. So there are some fundamental reasons for that. An object that has more than 75 times the mass of Jupiter undergoes something that is called a nuclear fusion in its core. And that's an important part of what a star is. It provides it with a lot of energy so that it can remain bright for a long period of time. And brown dwarfs don't have this. You probably know that giant planets also don't have a source of energy like this. So this is just to reinforce the fact that brown dwarfs are kind of in between objects, between exoplanets and stars. It's quite recent that we are able to study brown dwarfs. So what I'm showing you here is a graph that shows how many brown dwarfs we know as a function of time. So the first brown dwarf was found around 1995. And since then, we've discovered many, many more. So you can see that we now have several thousand. This count stops at 2015 because right now there isn't a very clean compilation of all the brown dwarfs we know. It would probably be above 4,000, the total number of brown dwarfs we know. It's quite a big task to collect a list of all of them because there's many publications that find new ones. So one would need to dig through all of the literature. And that's why we don't have a more recent update here. It's kind of a similar evolution to that of exoplanets. So the number of non-exoplanets already follows a similar explosion that dates from the 90s, and we now know several thousands of them. And there's a reason why these two fields of research evolve approximately at the same rate. So I'm having trouble changing slide here. Okay, so all of this is related to the fact that they are cold objects, much colder than stars. This is the case for exoplanets as well. So if an object is very, very cold, the light it's going to emit moves to redder colors. And at the extremes, it becomes invisible to the naked eye. And then you need to use infrared detectors to actually see these objects. It's a bit like a hot iron. So if you look at a spot on this image where the iron is really, really hot, the light that it emits is going to look white. And then as you move away to regions that are less and less hot, you're going to see orange and then infrared colors. And the same happens with stars. So stars that are very, very cold, we don't see any light coming out from them at visible wavelengths of light, but we could still see them at infrared wavelengths. So brown dwarfs are example objects that are so cold we cannot see them with the naked eye. So this is an example of an image seen with visible light on the left and infrared light on the right. And this shows you an example of the human body that does not seem to emit light at visible wavelengths, but it does still emit some light at infrared wavelengths. As you can see here, you can see in the right frame the hands of the person shining through the black bag. So the hands are actually emitting light at infrared wavelengths there. And it's really the same thing with brown dwarfs. They are so cold that they do not seem to emit light at visible wavelengths. But if you look at them with an infrared camera, suddenly you can see them. So brown dwarfs can form exactly like stars do. So that means you have a very large cloud of interstellar gas that starts to fall into itself along some filaments and form stars one by one. So that's a simulation of physics of what happens there. You can see the little white circles are stars being born in this molecular cloud. So basically, what happens there is that you're going to form a lot of stars of all masses. Some of them are going to be really massive, others are going to be small. And you are also going to see brown dwarfs forming in such an event. The number of brown dwarfs that get formed is smaller than the number of stars. So these objects are a little bit more rare than stars, but they can still form like that. So one thing we actually don't know is what is the smallest mass a brown dwarf can have. So what would be the smallest brown dwarf that could form in a scenario like I just showed you in a star formation event? We don't know how small a brown dwarf can be, but different models of the physics involved make different predictions. These predictions range from about 1 to 10 times the mass of Jupiter, but we don't know what the real answer is, and we're going to need some observations to really know for sure. We have actually found some objects which we think have masses as small as 4 times the mass of Jupiter, and they are freely floating around in space. So that could mean that objects this small could form like stars, or it could mean that they were ejected from a system of exoplanets. So they could have formed around the star and then be ejected. However, that's expected to be much more rare. So we don't know yet what these objects are, where they came from, but we're just starting to discover these kind of weird objects. If you remember, I said earlier that brown dwarfs are defined as being between 13 and 75 times the mass of Jupiter. So this object would be too small to fit the definition of a brown dwarf, but we don't actually have a good name for these kinds of objects. So I'm coming back to this slide where I showed you the range of masses. So we have so far a few objects with masses between 4 and 10 times the mass of Jupiter, for example. And by that definition, based only on the mass, we would call them giant planets. But the International Astronomical Union has in its definition of an exoplanet that it has to be in orbit around a star. So these kinds of weird objects actually don't fit any definition we have. So there's several names that have been used to describe them. If you start at the most boring end, at the bottom, you have isolated planetary mass objects. This is a very long and not very appealing term that actually makes sure you don't say anything false. So they are isolated. They have the mass of a planet, but we don't know what they are. Other names that have been suggested include sub-brown dwarfs, but they haven't been used by the scientific community much because they're confusing. There are some stars that are called sub-dwarfs, and there are some special classes of brown dwarfs that are also called sub-dwarfs. So if we were to call them sub-brown dwarfs, it would be very confusing. So because of this, pretty much no one is using this definition. I really like the definition planemos because it's shorter and it's clearly different from everything else. And it's actually a contraction of isolated planetary mass object. Planetary mass object is planemos. So I personally like that definition. Some other scientists have also called them free-floating planets. I try to avoid this definition because we don't actually know if they were born as exoplanets and then ejected, or if they formed like a star. So I tend to sit in between and use the word planemos. So basically, if you're at a conference and you want more intense reactions from the science community, you would use the terms higher up. So people are like mad or happy if you use the term free-floating planets. And people are pretty much, how would you say, don't have reactions if you use the word isolated planetary mass object. So if you want to be really safe, you can use that term. That's a term we use in scientific publications. So, oh, I'm sorry, I forgot to translate the title here. So what that should say is planets and brown dwarfs actually cool down as they age. And I'm going to just exit for a second and skip a few slides here because I know what happened. This is sub-slides that were left there. So let's go back here. We're going to go back to this, what this slide was mentioning a bit further. So I want to come back to how these objects can form. And it is true that these objects could be formed in a system around a star or even a binary star and then ejected in space. But I mentioned that this is actually hard to achieve. So you could have a system with 2 stars and a giant planet that starts in this configuration here. You have 1 star in red, 1 star in blue, and a giant planet in black. And if they have the proper configuration, it can actually be unstable. And I'm going to show you now what happens if you let this evolve through time. So you have the stars that are in orbit around each other, and the planet is getting actually exchanged between the 2 stars. And at some point, it's even going to get ejected completely from the system. So this is what we would call a chaotic system because it's unstable. And that is one way you could form a giant planet and eject it into space to create a free-floating object. And in this case, we could actually call it a free-floating planet. But if you wait long enough, we won't be able to know that this actually came from a star system. So we won't actually know where it came from. Oh, I have this problem again. Sorry about that. Looks like this got copied around. So it's hard to know the mass of a brown dwarf when we find it floating in space. The reason for that is that they cool down with time. So I mentioned earlier that brown dwarfs don't have nuclear fusion reactions in their core. And that's because they are not massive enough for their core to become really, really hot and under pressure. And because of that, they start with a finite amount of energy, which they got during their formation. As the gas contracts, it becomes warmer and warmer. And then they start with this warm temperature, but then they just emit some infrared light into space. And by doing that, they lose energy over time, and they become colder and colder into space. So as you, if you would graph the temperature as a function of time, it just slowly decreases. So this means you could have 2 objects that start at very different temperatures, and then they're going to decrease over time. But if all you know is the temperature of an object, you cannot say what it was. Was it a massive brown dwarf, or was it a very small mass object like a planemo? And in order to make the difference between the 2, you have to know their ages. So if you know that an object has a temperature that goes along the blue line here in this graphic, you don't know whether it's a very old brown dwarf that started with a lot of energy and had a long, long time to cool down. So it could be a very old brown dwarf, or it could also be a very young planemo. So it's an object that started with a lot less energy, but it had less time to cool down because it's very young. So age is really a key component to know the mass of these objects. We don't have this problem with stars. Because stars remain very, very bright for a long time, we can basically use their light properties to determine easily what their mass is. And we can't do that for brown dwarfs. So there are 2 ways we can know the mass of a brown dwarf. Either we find it in orbit around a star, and we study its orbit. We wait as it orbits around the star, and we make measurements of the brown dwarf and the star's velocities and positions and how they change over time. And by reconstructing their orbits, we can use some of the fundamental laws of physics called Kepler's laws to derive the mass of the brown dwarf. This is the most accurate way we can do it, but if we find a brown dwarf that is just freely floating in space, this is impossible to do. So then we have to make a prediction that is based on the age of the brown dwarf. But this is a problem because it's very hard to measure the age of an object. This is true for stars, but it's even more true for brown dwarfs. If you find an object in isolation and you study its light properties, you're basically going to have a really, really hard time determining what the age of that object is. So we have to find a way to know the age in order to make a prediction on what mass this object has. And one of the best ways to do this is to use young associations of stars. So basically, in this video, I'm going to show you a 3D view of the neighborhood of the sun. So we're going to approach the neighborhood of the sun. The sun would be at the center of the green circles here. The largest green circle is 100 light years in size. And all of these bright stars that I show around here are all young associations of stars. So there's actually something like 20 associations on top of each other here. And they each formed from the same molecular cloud. They each formed from a distant molecular cloud, which means that all the stars that are part of a young associations, they all have the same age approximately. They were all born within 1 or 2 million years from the same cloud of gas. And they all retain the same velocity as the cloud of gas. So the cloud of gas just collapsed into a group of stars that all kept moving in the same direction as the cloud did before they formed. So I'm going to show you this simulation, this 3D view again, because I want you to focus on what happens when I settle in the galactic neighborhood, and I'm going to turn on the time. So you're going to see where the stars are moving with time about now. Oh, not right now. So now I'm just rotating the view around. And when I turn on time, you're going to see where the stars are headed. And you're going to be able to notice that clumps of stars move together. So it's clear on the left, there's a few clumps of stars. And there are also other more diffuse streams of stars. We call those moving groups. They're similar to a young association. They're just less dense. And they're also all moving in the same direction. And the reason why they move in the same direction is really just because they keep the same motion as the cloud they have formed from. However, after a couple rotations around the galaxy, they're eventually going to get mixed up. The stars are getting perturbed a little bit by the other things they encounter along the way, and their velocities are going to be randomized slowly. And after a few 100 millions of years, they are so randomized that we cannot recognize which other stars that were their siblings, basically. So you can only tell that a coherent group of stars were born together if they are sufficiently young. So they have to be less than a few 100 million years old. Otherwise, they got mixed in the galaxy, and it's too hard to say which star they formed with. So I'm going to show you a little toy simulation, if you will, where you have a cloud moving around the galaxy along its orbit. It's going to form some stars. And the stars are going to initially move in the same direction than the cloud, but they're eventually going to get randomized. So that's what happens here. You have some stars. They initially have the same orbit, but then they disperse away, and then they become very well mixed, and they have velocities that seem just random. So you have only the first rotation or so around the galaxy to be able to recognize them as a coherent group of stars. Here, I want to show you some examples. So instead of seeing things in 3 dimensions like I did before, I'm showing you maps of the sky. So you could imagine a flat map of the Earth, This is similar, but I did that for the sky instead. So these maps show the whole night sky. And in the maps, I'm showing you each star that is a member of a young group of stars as a red dot. So these are 4 example associations. And you can see that their members are spread on relatively large areas on the sky. And the red lines are the directions of motion they are moving towards. So in reality, they are moving around the galaxy, but if you look only in the neighborhood of the galaxy, their orbits are almost straight lines. The difference here that makes these lines look curved is just based on geometry. So imagine you have a flock of stars moving past us in the Milky Way. If it's large enough that it passes through around the Earth, you're gonna see all the stars that seem to be moving all in the same direction in the sky. And as they get far enough, they're gonna get smaller and smaller on the sky as a clump. And that's basically what happens with these young associations of stars. You're gonna see AB Doradus, the one on the lower right, is the most interesting one. If I turn on the dimension of time, oh, I have to do it 4 times. You can see that at some point, they are spread everywhere on the sky. And this is actually the present moment is about this snapshot for AB Dor. So right now, this is where all the stars in the AB Dor group are distributed on the sky. So if you only look at their positions, they just seem to be everywhere. And basically that's because AB Dor is currently passing around the Earth. So the Earth is almost in the center of this association. And if you look in any direction, you could find some of its members. And because of that, it's very hard to recognize the members of AB Dor. You really have to look in what directions they are moving to actually recognize that it's part of this flock of stars all moving together. So you really need to know their 3D velocities to realize that they are part of the same association. You cannot just use their positions. So you might be more familiar with the distant clusters like the Pleiades, where they are all in the same region of the sky, but that's really a consequence of them being further away. So if you took the Pleiades and placed it right around the Earth, it would become really, really hard to know which stars are part of the Pleiades or not. They would look like they are in any direction on the sky. So as you can expect, we need to measure the velocities of stars to be able to tell in what young association they are. So this is an example of how you would measure some components of the velocities of a star. This example is Barnard's star. So you just take snapshots of the sky and wait. You're going to see the star move around. So you are getting 2 components of the 3D velocities of the star by doing that. So imagine the Earth, I don't know if you see my screen, also, my image or just the screen, but you can imagine the Earth looking at Barnard's star as it's passing around. You're seeing the direction of Barnard's star in the directions that are tangential to the line between the Earth and Barnard's star. So you're seeing 2 components of the velocity, but you don't know how far Barnard's star is moving towards us or away from us. It could also be moving towards us as well as tangentially. So this is just partial information. So we need to do this with infrared cameras if we wish to discover brown dwarfs in these young associations. So just to have you recall, we want to find brown dwarfs for which we know the age in order to be able to tell what mass they have. And the best way to do this is to find brown dwarfs that are part of these streams of stars, these moving groups, also called associations of stars. So we have to study their motion with time. So we need to take infrared surveys that took images of the whole sky in the infrared, and we need to see how they move around as you wait. In other words, you need to have more than 1 snapshot of every region in the sky. and they have to be spaced away by enough years for the stars to have moved around. So the stars that are closer to us tend to move farther just because of the parallax effect. You see the motion more clearly. And the stars that are more distant in the background don't appear to move as much. So this is an example of a snapshot taken by the 2MASS survey. So this is an infrared camera that mapped pretty much the whole sky in about 98. And this is a different image taken by the WISE spacecraft in about 2010. This is a spacecraft that works in space. So it's a bit more efficient. So you can see that there's more stars in WISE versus 2MASS because it's more sensitive. It's better at seeing very, very far things. However, there's something interesting that you can see if you focus on the two images enough and you flip between them. The star near the center has actually moved slightly with respect to the other stars around. So let's circle it. You can see that it's moving to the lower left in the image. And that's with about 12 years difference between the two images. So you can see it's not a very drastic motion like the case of Barnard's star, but it's still enough that we can measure it very precisely. And this gives us two of the three components of the velocity of this object. So it happens that this is a brown dwarf. And from these two images, we can derive the velocity of this brown dwarf in the direction that is tangential to Earth. So what my team did to recognize brown dwarfs that are members of these young associations is automatically analyze a very large numbers of these matches between the two different categories. What we need to do then is use some advanced statistics to basically determine a probability that it has a velocity that matches one of the associations we know about. So remember, we don't have the 3D velocities completely because we don't know if the brown dwarf is moving towards us or away from us. So we are missing one component of the 3D velocity, but we can still check whether the components that we see match any of the young associations of stars. So basically we are asking, is this star moving in the sky toward the same direction than other members of Abidor, for example? And if it is, then it becomes a very interesting star, and we're gonna use telescope time to observe it in more details. So by doing this, we were able to find about 300 objects that we think might be planemos. So this means if they match the young association that they seem to match, we can derive their mass, and their mass seems to be very small. So less than 13 times the mass of Jupiter. So it's by doing this kind of analysis that we are able to identify potentially new planemos. There's another way to do it, and it's to use human eyes. So the human eye is typically much better at recognizing moving objects in a set of images than current algorithms are. So one of the really strong forces of human vision is recognizing patterns. So we're starting to get there with machine learning algorithms, but it's a very slow progress. And we're at this weird moment where human eyes can really help advance science. So some of my collaborators and I have set together this project called Backyard World's Planet 9. And what this project allows you to do is to actually look at many snapshots of infrared images taken by the WISE spacecraft and try to spot objects that move in these images. And citizen scientists have done this to identify something like thousands of new brown dwarfs. So this particular project does not only try to recover planemos, it's really interested at discovering all the brown dwarfs in the neighborhood of the sun. But then I can look at this catalog of brown dwarfs discovered by citizen scientists and pick out which ones have motions that match a Young association of stars. And that is a second source for me to find new planemos. So there's the automated surveys, and there's the human eye surveys like that of Backyard World's Planet 9. And that means if you go to that URL, you can also start searching for new brown dwarfs and potentially new planemos too. So just to summarize, there's two approaches, the automated approach and the citizen science approach, like Backyard World's Planet 9. And then there's more work to be done before we know if we found a planemo or not. So we need to go at the telescope to further investigate what we think might be a planemo. So one of the telescopes I use to do this is Magellan in Chile. And what this allows us to do is separate the wavelengths of light that we receive from that object. Like the Pink Floyd logo, basically you pass the light through a prism and it separates them into all its colors. And then you can study the intensity of each color. And this can tell you many, many useful things about the object. It can tell you its temperature quite precisely, and that's already a start to be able to know what the mass of this object is. We, in advance, when we select our objects, we make sure they are invisible at visible wavelengths. So basically the human eye could not see them. And that ensures they are very cold. Basically it ensures they're not just stars. But by splitting the light like that across all its wavelengths, we are able to get a more precise temperature. And you might also have seen in some physics classes that if you have different elements, they are going to leave different fingerprints in such a rainbow that is generated by splitting the wavelengths of light. So if you look carefully in the image at the lower right, the authors that built the image also added some dark lines across the rainbow. And this would be an example of the fingerprints of a molecule or an atom. So in this example, for example, maybe it is hydrogen, and hydrogen leaves this fingerprint in there. And we can recognize these fingerprints, so we can reconstruct what elements are there in this object and how abundant they are. So which elements are more present in the atmosphere of the object or not. This allows us to really see the atmosphere of the object only. And it allows us to know what elements are in its atmosphere. And from this, we can have an indication of what the pressure is in the atmosphere. And that tells us indirectly about how strong the gravity is in the atmosphere of this object. And sometimes it can give us hints that the object has a lower mass than what is normal for that kind of object. That would be one first sign to suspect something is a planemo. If it has less mass and the same radius, it is less dense, and the pressure will be lower in the atmosphere. So we get all kinds of information from this. And on top of all these things, the fingerprints of an element shift around to bluer or redder wavelengths if the object is moving towards us or away from us. This is called the Doppler effect. The same thing happens with sound. When a car moves towards us, the sound gets, the pitch changes as an object moves towards or away from us. The same thing happens with light. So the whole rainbow that you see there, it moves from bluer to redder colors as an object moves towards or away from us. So this actually gives us the key to know the full 3D velocity of this object. Remember, we had the two components of velocity that are tangential to our to where we are looking at. We were only missing the component of velocity that is towards us or away from us. And now that we know the three components, we can reconstruct what the 3D velocity is of this object. And this allows us to test with a lot more accuracy whether the object is a member of a Young association of stars. Another thing that we do is we go at the Mont Mégantic Observatory to take more measurements. So there's basically, we look at how bright the object is with different filters to get a more precise temperature too. And we also look at how the object moves with time. That allows us to know the proper motion, to confirm the velocity of the object that we suspected from the WISE spacecraft. But it also allows us to measure the distance of the object. So basically, with the WISE spacecraft, we typically have only about 5 snapshots that are distributed from 2010 to maybe 2015. And that gives us some measurement of the velocity of the object. But we can get more precise measurements if we go at Mont Mégantic and take, let's say, 100 epochs instead of 10. So we can keep observing it way more often than what the spacecraft was able to do. And that allows us to refine the proper motion. But even then, if you wait more than a year, as the Earth rotates around the sun, you can see objects wobbling around on the sky. This is called the parallax effect, simply because the Earth is moving around. And the very distant stars don't appear to move, but the near stars are going to appear to wobble because of this geometric effect. And the closer a star is, the more it's going to wobble with respect to the background stars. This is actually one of the best ways we have to measure the accurate distance of a star. So this is another important measurement that allows us to determine if a star or a brown dwarf is really a member of a young association of stars. So by knowing its position, its distance, its proper motion, which is how the star moves on the sky with time, and the radial velocity, which is how fast it moves away or towards us. By knowing all of these things, we can get a very accurate measurement of their 3D position in the galaxy and their 3D velocity in the galaxy. And that really is key to know which ones are members of young associations. So those are all measurements we need to confirm at the telescope. So just to summarize, we measure temperatures, distance, 3D velocities, chemical composition, atmospheric pressure, and we can even see whether the object has clouds by splitting the light across all its wavelengths. So this allows us to know a lot more about the object. So we only know about 6 planemos to date that are quite secure. There's one that was discovered by the Pan-STARRS survey in Hawaii. There's 3 that were discovered by automated surveys carried by our teams. And there's one that was actually found by the Backyard World's Planet 9 project, the last one on this list. And another one that was found by a researcher called Kevin Luhmann, who did this by eye alone. So that's quite crazy. He inspected millions of images of the WISE telescope by himself, and that allowed him to find another one of the known planemos. And I'm gonna tell you about some of their characteristics because they're very different from each other. They have very varied properties. So one of those that our team discovered is 11 times the mass of Jupiter. So it's almost a brown dwarf. It would need to have 13 times the mass of Jupiter to be really called a brown dwarf. It's 62 light years away from us, and it's really cold. So it's what we call these brown dwarfs T-type brown dwarfs when they are that cold. And that means they don't have clouds in their atmosphere. And if you were to look at them with infrared eyes, like those of the 2MASS survey, they look pretty blue, which is because they are very cold. There's another one we know, which is called SIMP 0136. This one is really nice because it's very nearby. It's only 20 light years away from us, but it's right at the boundary between planemos and brown dwarfs. It's about 13 times the mass of Jupiter. It's a bit warmer than the previous one, and it has very, very thick clouds in its atmosphere. This object has been studied a lot at the Mont Mégantic Observatory, even before we realized it was a planemo. So we thought it was much more massive before, and we kept observing it because it's so interesting. As it rotates on itself, we can see patterns of clouds changing. And on top of that, the clouds are moving around. And because of this, the light of this object keeps changing. It becomes brighter, fainter, And studying all of these patterns of light is telling us a lot about the weather on the surface of this object. And that's why we have been observing this for years at the Montmégantic telescope. So when we realized it was actually a planemo, we were quite excited. Another example is the one that was discovered by Kevin Luhmann alone, is an extremely cold object. We actually don't know its age, but we know it is a planemo because even if it's as old as any star in the Milky Way, it still needs to have a mass smaller than 13 times the mass of Jupiter to be this cold. No brown dwarf would have had the time to cool down to such crazy cold temperatures. So we really know it has to be a planemo. And this is one of the most crazy objects. It is only at about 6 light years from the sun. It is one of the nearest objects we know to the sun. It's like, if you count the nearest stars, there's like Proxima Centauri, I forget which star is the second nearest, but this object would be fourth, only the fourth nearest object to the sun. So remember, it's not in the solar system, it's outside the solar system, but it's in our most immediate neighbors. And this object probably has about the mass of Jupiter and the temperature of Jupiter. It is extremely cold, and we think there might be some water condensing in its atmosphere into snow. So based on some observations we have, we think that its upper atmosphere is very close to 0 Celsius, which means water is becoming snow. So this is like we have some kind of a cousin to Jupiter that is just floating around really, really close to us. And either we are extremely lucky that there is one object like that so close to us, or they might be very, very common. And we just see this one because it is close enough for us to see it. It is extremely faint. We can't see it from the surface of the Earth. So my colleague, Jackie Faherty, tried to get an image of that object from the Earth. She used the Magellan telescope, which is a 6.5 meter infrared telescope in Chile. And it took her something like 3 nights to get a very, very faint detection on this object. So it's really almost impossible to see it unless you are in space with an infrared telescope. So that's why it took so long to find it. That's why we didn't know about it, even if it was one of our closest neighbors. It was discovered around 2012, if I'm not mistaken. So it's a very recently known object. So this is an image of the sun with the Oort cloud. So the Oort cloud would be the very, very exterior of the solar system. So and anything outside of the Oort cloud is really outside of the solar system. And those are the nearest systems known to the sun. So there's Alpha Centauri with Proxima Centauri, which are in orbit around each other. There's Barnard Star, which is the second closest. And then there's a brown dwarf binary that was also recently discovered. And the fourth one that is squared in white here is WISE 0855, which is this crazy object that is a planemo. This object was discovered by WISE, which is pictured here. So if we look at all of the currently known planemos, you can place them in the dimension of age horizontally and temperature vertically. So in this image, everything that is higher up is warmer. Everything that is further to the right is older. And the red circles are the currently known planemos. So you can see that we know 2 of them that are extremely cold. We know the other 4 of them are very young. So they are hundreds of millions of years or younger. Which is young at the astronomical scale. And I've added as white circles here some more potential planemos that are still only candidates. They need to be confirmed. And each red line in here corresponds to 1 mass of brown dwarf or planemo and how it cools down over time. So if you take the lowest red line here, it corresponds to how a 6 Jupiter mass planemo would cool down over time. So it starts relatively warm at 2000 Kelvin, and then it's going to cool down over time as it ages. So it's by placing objects on this graph and comparing it with the lines there that we can deduce their approximate masses. And the lines are actually built by modelers, so based on the fundamental properties of physics, how fast these objects are expected to cool down. So one reason why planemos are so interesting to us is that there's no bright star that is right next to the object, completely blinding us. So we can study them in much greater details. This is an example of an image of the star HR 8799. This is a very popular star because it has a system of giant exoplanets in orbit around it. And this is an image of the star taken by the Hubble telescope. And what we see here in that image is only the star, the central star. And it's so bright that it's creating this really big region on the detector. And it's because it's bringing out all of the micro defects in the lenses of the telescope. If the telescope was perfect and gigantic, we would only see a tiny dot of light. But because it's not infinitely large and it has microscopic defects in its lenses, we're getting a big region of light like that. And the giant planets around HR 8799 are actually inside of that bright structure. So we need to do some really advanced image processing techniques and take a lot of different images to actually bring out the planets that are hidden in the bright light of its star. So this makes it really hard to study these giant planets. Even though we can see them in this image, it's hard to measure their brightness very accurately. And it's even harder to split their light into all the different colors and do a detailed study of their atmospheres. So Planemos allows us, any Planemo allows us to do that way more easily. We don't need crazy subtraction methods to remove the light of the star. And we end up with way more precise data. So that's basically what I was explaining. You can way more easily split the light of a planemo into all of its colors because it's not contaminated by a very bright star right next to the planemo. So the best images we have of a planemo looks like that. It's just a dot of light. So if you see some pretty images of exoplanets or planemos in press releases, they're always artist conceptions. The best we can do is see a little tiny dot of light because these objects are just too far from us to see what they actually look like. We can deduce what their properties are from splitting their light in many different colors and doing analysis of their light. But what we see on the detector of our telescope is always just a tiny dot of light. So those are examples of known giant planets that are in orbit around the star. And here again, all we can see is a blob of light. So we can see the light emitted by the star and the light emitted by the planet a little bit further away. And all the planets in these images are just small red dots. So we don't see any features on their surfaces. So something relatively new that happened in these projects is the launch of the Gaia spacecraft. So in 2018, it published something really important that completely changed our field. So it measured the distances of 1 billion stars with a crazy accurate precision. It's way better than what we had before, and it's way more stars than what we had before in terms of how many stars we know the distance. So in only the 3 years since it published this first data dump, basically, there was almost 2,000 publications based on these data. So it's a wildly popular set of measurements that completely changes our understanding of the neighborhood of the sun. So now we are able to know really precisely the distance and the motion of the stars around us. However, this is a mission based on visible light. So it does not detect brown dwarfs. So it's really only focused on stars, but this is still important to me because it allows me to better understand young associations of stars and discover new ones. So those are new laboratories to try to find planemos after that. So this is an example of the Milky Way and where we are in the Milky Way. And each circle here tells you how far Gaia was able to measure distances to the stars with a different precision. So for example, the blue circle shows you all the stars for which we have a 1% precision, which is really, really accurate. And if you go up to 20% precision on the distance, you go all the way to the red circle here. So this shows you how we are able to know the distance to stars in a very large bubble around the sun. And this is a 3D view of the stars around the sun as based on the data from Gaia. So this has time turned on. So you can actually see where the stars are moving. So time is really sped up a lot here because star moves on the order of millions of years. So you are probably seeing something like 1 million years per second here. But we would never have been able to do such a visualization before Gaia. So we knew the distances to maybe a couple 100,000 stars. They were not very accurate, but now we know the extremely accurate distances to a large number of stars. So for the first time, we are actually able to see all the stars around us in 3D and how they move. And as you might expect, this is really valuable to discover new streams of stars that are moving together because they formed from the same molecular cloud. So this is extremely important to the study of young associations. This is another really cool thing we can see with Gaia data. So if you look at all the entries in Gaia and turn on an image of the Milky Way, and then I'm gonna approach it and turn the image of the Milky Way on and off, you can see gaps in the Gaia data where there are gaps in the spiral arms of our galaxy. So we are actually seeing some imprints of the spiral arm structure of the galaxy by just making a simulation where we place every star with its accurate distance. So we are beginning to see really some structure of our galaxy only based on the positions of stars. This is a visualization of all of the known young stars that were closer to about 300 light years of the sun before Gaia and after the publication of Gaia. So it basically doubled the amount of young stars that we know around us. And you might notice that a lot of the stars that Gaia added are redder, and those are based on the real colors of the stars. So it's approximately what our eye would see as a color. And the reason why most of the new stars discovered by Gaia are redder is because they are smaller, fainter, redder stars. So less massive stars are smaller and they're colder in temperature. And because of that, their light appears redder to us. And they are harder to study because they're fainter. And that's why we didn't know their precise distances before. And it's really the advent of Gaia that allowed us to recognize which ones are parts of young associations. This is actually just something like 3 months after the big data release of Gaia. So this was called the second data release in September 2018. So we are also uncovering some really exciting stuff in Gaia data. So there's a known clusters of relatively young stars that is called the Hyades, which you might have heard about. It's very near us, it's not very far. And in this image, you can see the position of the Hyades star as if you would be looking at the galactic plane from higher up. So it's the position across the galaxy, it's called X and Y. And so it would be the center of the galaxy would be very far to the left of this figure. And the red points here are the known members of the Hyades. So they're very grouped together, as you could imagine for a cluster. And Gaia allowed us to discover all of these blue and green stars in this image, which are actually tails around the Hyades cluster that all move around in the same direction as the Hyades. So actually, there are many more stars than we previously thought that are born at the same time as all of the Hyades stars. And all of these blue and green regions are therefore new places where we can try to find new planemos. So any new structure that we discover, which are of the same age, we can all use them to age date brown dwarfs and realize they might be planemos instead of brown dwarfs. So they are all very valuable additions every time we can find new structures like that. So this actually also happened for two other clusters, Praesipi and Coma Bear, also now are known to have tidal tails like that. And this is a 3D view of these three clusters. So they all look quite similar. You can see that they are slowly getting torn apart along these tails as they move around the galaxy. So we are actually seeing clusters in the process of being dissolved and randomized in the galaxy. We also think we might have discovered a very large tidal tail to another cluster that is close to us. This cluster is called Ursa Major, and it's actually made up of the stars in the Ursa Major constellation. So the Big Dipper, basically. So a few stars in the Big Dipper are actually part of an association. They were born together and they move in the same direction. But there's something mysterious about this cluster because it's slightly older and it only has massive stars. It only has some of the most massive stars that are possible that remain in this cluster. And we think that this is because this cluster is older and it has had time to move around the galaxy a bit more. And all of its lower mass stars were torn away from it. So the more massive stars at the center of the association are a little bit harder to remove. And because of that, now all that we can see anymore is the massive stars that are there. So for the longest time, we had no idea where the low mass stars of the Ursa Major association might be. But now we are starting to see these gigantic structures that are thousands of light years in size around us that are also moving in the same direction as the Ursa Major cluster. And we think that those are older tidal tails, like those that we saw for the Pleiades and Coma Bear, that are just diffused further away. And we have started some telescope follow-ups for some of these stars that we think are part of the Ursa Major. So I'm showing it here in red stars in this figure. Those are all stars that we are currently trying to observe with the Canada France-Hawaii telescope. And we want to confirm that they have all a similar age, basically. So let me show you in 3D these potential tidal tails to the Ursa Major cluster. So this is Ursa Major. So this is the small group of very massive stars that move together that we think is the remnant of the cluster. And now I'm going to turn on the tidal tails that we think we might have found. So those might be all of the low mass stars that were once part of this cluster, and they are all getting torn away and diffused away from the cluster. And if I was to turn on the time, they would all be moving in the same direction with each other. I can't recall if I actually did that in the 3D video, maybe not. No. So this is another figure that shows you a view from above the galactic plane centered on the sun. And all of the circles with different colors are known clusters of stars around the sun. And with new data from Gaia, we were able to actually target new ones and discover entirely new clusters that we didn't know were there. So those are some of them in red stars here. So those are especially exciting because they're brand new places we can start looking for planemos in. And this is another more recent study that showed it's a similar idea. It tried to discover new clusters of stars, And what's really exciting about that is that it not only discovered new clusters, but it also discovered streams, so very, very elongated structures of stars that all move together. And that's a bit, reminds me a bit of the tidal tails around these clusters. So they might be groups of stars that are slowly dissolving around us. So those are potentially even more regions where we can know the ages of stars based on their membership to a young association. This is a 3D view of the same data set that I made. So you can see all of these clusters around. And the strings are a little bit less obvious because they're less dense and they overlap with each other. But that shows you a view of plenty of new clusters we're discovering around the sun. And today, actually this morning, there was a new data release from Gaia. So it's called the early data release 3. And it's basically an even better version of all the Gaia measurements. So it's more cleaned up, the data is better, accuracy is better. So I'm currently working hard to see if there aren't new groups or new things to be discovered in this data set. So here I'm trying to show you a 3D view of all the stars within, this one is 300 light years. So it's a little bit slow because there's many, many stars in there. But you can see this is centered around the sun, and this shows you how many stars there are. It's really, really populated. This makes it really hard to find clusters because all we can see are only the most massive clusters. Here you can see, I think this one is the Pleiades. So you can see a slight overdensity to the left, which is the Pleiades. But you wouldn't be able to see any of the other associations I discussed today because they are too spread. They're too spread apart. They don't come out clearly as an overdensity. So it's very hard to find them because there's just so many other random stars that are floating there. So that's it for my presentation. I hope you enjoyed it. And if you have questions, feel free to ask them. You can also have a look at my blog. So on my personal webpage, I have started writing a blog about my research. So for example, I wrote one about the new tidal tails we think we have found around Ursa Major. I go into a lot of details. It's not like a very short blog post like a press release, but I try to use very approachable language and avoid technical terms or explain them. So this way, even the general public can try to follow what we are doing. And I also have a blog about coffee, if you're interested. That's an example of a blog I wrote recently about the planet AU-MIC-B. So this is a planet we found around a very young star that is it's a member of one of these young groups I've been talking to you about today. And this is a blog where you can read about how to improve coffee preparation if you're also passionate by coffee like me. So thank you.
Jonathan, thank you very much. Just when you think it's safe to start looking at stars again, it then gets very, very complicated and even more intriguing. Could I ask you to stop sharing your screen, please?
Sure.
Okay, and as people are thinking about their questions, once again, ladies and gents, a blue hand for a question would be appreciated. Otherwise, wave at me frantically. We've got 30 odd people logged on, so I might have to scan up and down the view. While you're thinking of your question, one from me, Jonathan, where does the term hot Jupiter fit in with all of your descriptions?
So the term hot Jupiter is used in context of giant exoplanets that are very, very close to their host stars. So they are objects quite similar to those that I study, except that they are being completely overheated by the heat of their star. And that causes them to puff up, to become warmer, and to become extremely large because of it's basically the impact of their host star. So they are orbiting so close to to their star that they are getting really, really heated up. So the objects that I study are not getting heated up by anything because they are isolated in space. But hot Jupiters are really extreme cases. Most giant exoplanets are not being heated like that by their stars. So hot Jupiters are much closer to their star than even Mercury. They're really, really odd objects. So the first one that were discovered were completely surprising to astrophysicists. They were a total surprise that even the modelers of exoplanet formation struggled with for a long time.
Okay, thank you for that. That's cleared that point up. So, ladies and gentlemen, I'm looking for people with questions. If you've got
I see one in the chat already. Someone said, Nigel Satterley said, are these floating planets the gravity pull from its neighbors? Would discuss total stabilization issues and more as far as we know. I'm not sure I understand very well, but I think what Nigel is asking is whether the floating planets are significantly attracted by other stars around them. You can correct me if that's not right.
Nigel, can you unmute yourself, please?
Yeah, that's correct. And what Jonathan's saying, yeah. I thought there may be major disturbance and like a ping pong effect from these exoplanets as they move around. I just wondered if that could cause what we call major damage as they go around.
So on average, if you would take a snapshot in a moment in the life of a planemo, the nearest star around it would be way too far for the planemo to feel the gravitational pull of the star. However, as the star moves around along its orbit in the galaxy, it might happen every maybe few 100 million years that it passes close to a star. And when that happens, the star might pull a little bit on it and change its orbit a little bit. So because of that, a planemo that goes around the galaxy for a long, long time is going to get perturbed away, a little bit like a ping pong ball, but it's in a different context. It's rotating around the galaxy. And from all of these very rare events where a star pulls on it slightly, there's going to be a collective effect over time where the planemo is going to have a larger and larger velocity, and it's going to move faster and faster. And it's going to look odd after a few billion years. And we actually know some brown dwarfs that are like that. We don't know any planemos like that. But we know brown dwarfs that are extremely old and that have odd velocities because they were tugged away by stars along their motion very often. This also happens with stars. The oldest stars tend to have large velocities. And this is also the process by which clusters and associations slowly dissolve over time. So they encounter stars, they encounter even sometimes another association. They can pass through each other and basically break the other one. So stars will very rarely collide. It's almost impossible to have two stars to collide because there's too much empty space. But they will sometimes pass close to each other, close enough to pull a little bit on each other. But keep in mind, those are rare events. It's only with the collective effects of these tiny rare events that you get larger velocities over time.
Okay.
Thank you very much. Thank you.
Mm-hmm.
Okay, Nigel. Roy, can you unmute yourself, please?
Yeah. Question I've got is, when these objects are formed in the universe from gas clouds, using the Hertzsprung-Russell, that the heavy mass things are very rare, and it gets more frequent down to the red dwarfs. There's a lot of them in comparison to, say, an A or an F-type star. Is it thought that there's more and more brown dwarfs because, you know, the low mass objects, so are they going to be more frequent than the, say, red dwarfs?
Actually, no. So this trend reverses when you go to smaller masses. So if you go to, for example, an a star with 8 times the mass of the sun, they're very rare, as you say. And as you go to smaller masses, you form more and more and more of them. But this trend only holds all the way to about 0.1, 0.2 times the mass of the sun, which are red dwarfs. But if you go even smaller than that, it starts to get rarer again. So even brown dwarfs are quite a lot more rare than stars. So if I recall well, it's of the order of, for each brown dwarf, there's about 10 stars. So it's this is not the exact number, and we're still improving it, but it's in this ballpark. So as you move to smaller masses than red dwarfs, then you get into the brown dwarfs, and those are rare, a lot rarer than the red dwarfs. And as you go to planemos, they're even rarer. But again, our statistics on how rare planemos are very shaky at the moment, because we only know 6 that are solid, and doing statistics with such a small sample is very hard. They're just really hard to discover. So I mentioned earlier that they're much easier to study, which might seem contradictory to what I'm saying now. But the problem with planemos is knowing where to point your telescope. Once you know where a planemo is, you can take an infrared camera and study it in all the details you want. The problem is figuring out there's a planemo there. You need to do some detailed studies to know it's not a brown dwarf, and to know that you need to know its 3D velocities, etc., which are hard to measure. So they're the kinds of objects where they're very hard to find, but once you found it, they're very easy to study in more details. So they become extremely valuable.
Okay, Roy. All right, Peter J. Can you unmute yourself, Peter?
Yeah, sure. Hi, Jonathan. Great to see you.
Hey.
Our end. How are you? You all right?
I'm good.
Oh, good. I have one question, and basically, I've sometimes looked this up on the internet, but is there a lot of evidence for any exomoons or companions to brown dwarfs or planemos, or, for example, systems forming around them? So I've had a look sometime on the internet. Doesn't seem to be many examples of such.
I don't actually know of an example with a planemo. The closest I could think of is a candidate planemo that is a member of the TW Hydra Association. It has an ugly name. It's called like 2MASS J1119. And we thought this was a 8 Jupiter mass planemo up until recently, but there's a recent paper by William Best, who observed it with a very high resolution telescope and noticed that it's actually a binary planemo. Wow. And what we thought was one bright-ish source in the infrared, he noticed it was actually 2 sources that are much fainter, half as faint. And because of that, their individual masses are actually around 4 times the mass of Jupiter, and they're in orbit around each other. So that's a really weird system, potentially a binary planemo, and that is a strong indication it must have formed like a star, because star formation is good at forming binaries, and it's extremely rare that you would see 2 exoplanets. Well, actually, we don't have any example, as far as I know, of 2 exoplanets that are like a binary, but in orbit around the star that formed in the disk of the star when it was young. That's really, really hard to do. And even worse, it would be really hard to eject such a binary planet without breaking the binary.
Yeah.
So this tells us that this object must be formed like a star, and that would put the lowest constraint we have ever seen on the smallest object that can be formed like a star, because you have 2 times a 4 Jupiter mass object. The only thing we don't know yet for this object is its precise distance. It's so cold that you cannot see it in visible light. And because of that, Gaia didn't measure its distance. We have a few programs that are trying to measure its distance with infrared telescopes, but it takes years and years. So we're still following it.
Thank you very much. Thanks.
Mm-hmm.
Okay, ladies and gents, I'm looking for any other questions.
I can add something too. There's a well-known brown dwarf that is young called 2MASS 1207. It's a more massive brown dwarf, and it has a planetary mass, a giant planet around it, basically. That's another example of a weird system. Those are rare.
I'm sure as resolution improves, they'll no doubt find quite more even smaller objects going down brown dwarfs, because I'm sure Jupiter's a good example in our own system of a miniature system.
Yeah.
So.
Yeah, they're extremely hard to detect because they're smaller, and they might be rare, but we don't know that for sure because it's too confused, because our technology doesn't allow us to detect them easily so far.
Yeah. Thank you.
Okay, ladies and gents, I'm looking around one last time for further questions. I don't see any takers. So, in our usual Mexborough and Swinton manner, can we thank Jonathan for an excellent and highly interesting talk. Thank you, Jonathan.
Thank you. Thanks. Very appreciated.